acá para que salga la cámara de luz, estamos acá en el piso. Así que, bueno, la charla de hoy la va a dar, bueno, Antonello Sbrizzi, que está acá en el programa, que la tuvimos que pasar del lunes pasado, que se cortó la luz. Para los que no lo conocen, bueno, Antonello ya es un amigo de la casa de hace varios años. Esta es la tercera vez que va a dar una charla acá. Con él, bueno, nos conocimos haciendo un doctorado en Holanda, cuando estábamos trabajando haciendo física de los mesones B, en el DAISY, en unos experimentos que están en Hamburgo. Él después siguió trabajando en el experimento Atlas del CERN, con vínculos con la Universidad de Bolonia, y bueno, ahora es el investigador del CERN, con lugar de trabajo en Ginebra, en el CERN. En los últimos años estuvo trabajando mucho en lo que es física forward, con los vectores que dentro de la comunidad se conocen como AFP y LUCI, donde también hacen mediciones de luminosidad, que bueno, fue de las charlas que nos dio las otras veces. Y bueno, ahora está acá, principalmente por vacaciones y bailando tango, pero bueno, aprovechamos que estamos por acá, invitamos a que nos visite y nos dé una charla de un experimento nuevo en el cual empezó a trabajar, que está ahora en el Instituto Rutherford de Inglaterra, bueno, con átomos de muones, y ahora nos va a contar de qué se trata eso, y bueno, después tendremos un café para seguir charlando. Así que bueno,
gracias. I will do it in English, so yeah, as Anand said, so this is an activity that I started since 2-3 years, and it's a side to the activity that I do at CERN. Yeah, and yeah, that I do aside to the work that I do at CERN. So it's an experimental physicist measuring luminosity mostly for the Atlas experiment at CERN. And then I started this activity so that I also take some satisfaction for the physics side. So for this experiment, I'm doing mostly analysis and development of one of the detectors for X-ray detection. And it's an interesting field of physics. It is low energy, so it's a completely different domain compared to the Atlas experiment. And then explain a little bit what we do with this experiment and the current result. So the idea is to work with muonic atoms. And muonic atoms are atoms where one muon takes the place of one electron, and start to orbit around the nucleon, but with a different energy level. And so the difference between the two energy levels corresponds to the energy of the X-ray that is emitted for the absorption of the neutron. So this emission of an X-ray is called muonic X-ray, is the signature of the formation of the muonic atoms. And the interest of muonic atom is that the muons orbit close to the neutron compared to the electron, also close to the nucleus. So it will be more sensitive to both the property of the nucleus itself as a whole and also the nucleon inside the nucleus. And the interesting is that the energy that corresponds to the difference between the two energy levels, so the energy of the muonic X-ray, it's about the threshold of typical instrument that we use to detect particles. One specific case is the muonic hydrogen. So it's the atom composed by only one proton and the muon around. So you see it's the orbit of the electron. So it's just a design, a sketch to repeat again that the muon orbit closer to the proton. And the muonic atom is just formed by one muon and one proton. And the idea is that we want to measure one quantity that is the energy of the hyperfine splitting of the energy level of the muon around the proton. When you get this hyperfine splitting energy, you will be able to measure the energy. And from this relation, from energy that you measured, or the splitting, hyperfine splitting, you can get a measurement of the radius of the Zeeman, radius of the proton. The other quantities are known to compute with a certain degree of accuracy. And when you measure the Zeeman radius, then you will be able to extract information about both the density, the energy, the density of electric charge, and the density of magnetic dipoles. So again, this is a measurement of energy, it's a measurement of a resonance, and we have developed an instrumentation to measure precisely this energy and extract the radius of the radius of the proton that is related to the energy. The target accuracy of the experiment is here in this picture. It's very small compared to the precision of the other experiment that has been published and to the phenomenological experiment that are on this table. So you see that the calculation, they are quite in agreement between each other, but yeah, the family will be able to measure with more accuracy. And it also, when I started this experiment, there was a famous, was called the puzzle of the radius of the protons, because it was a period in which not the Zeeman radius, but just the electric, the values of the electric charge of the proton was measured with two different techniques. And on one end with scattering of electrons, and on one end with the techniques of the muons, and they were giving two different results. But with the time, the result obtained with the muons revealed to be the correct one, because they triggered the reanalysis of all the experiment with electron that confirmed the value of muons. So that part is considered closed, then the physics program of the experiment is now more concentrated on this type of measurement of the Zeeman radius. So FANO is the name of the experiment and stays for physical diatomy knowledge. It's a collaboration that is dominated, so it's dominated by Italian physicists, but there are also other institutes from other European institute. And so the idea is to create the muonic hydrogen by stopping muons inside the gas. So you have a gas made of hydrogen, and you try to put low energy muons in contact with gas, so that these low muons will be absorbed by the hydrogen. So will be absorbed by it means that we will take the place of the electron inside the hydrogen, and so you form muonic hydrogen, and then with the laser energy at exactly the energy of the transition of the hyperfine splitting, that is 183 milli-electron volt. So if you put the laser with this energy in contact with the gas, then you will make the resonance. So you will excite the resonance of the hyperfine splitting. And then if you have, so far we have an experiment with the detector to be able to measure the resonance. So the some excess of activity that in correspondence to the formation of the hyperfine splitting state. And this measurement is done with scan. And then we will explain then how we do the scan. We need basically an experimental signature to make this measurement. And the experimental signature comes from an excess of X-ray. And this excess of X-ray is due to the fact that when you have formed the muonic hydrogen that you see here in the picture, then the muonic hydrogen inside that is excited lose this energy inside the gas, but lose with energy without emitting radiation, so it does not have a soft emission of photon, but it will collide with the molecule of the gas and will lose this energy. So we will found that this energy as an excitation of the molecule, so the molecule then will go faster. And the fact that the molecule will go faster, this will increase the probability of the transfer of the muon from the muonic hydrogen to the oxygen. So the idea of this experiment is to put a little quantity of oxygen inside the gas mixture of hydrogen, so that you will see an excess of muonic X-ray emission due to this increase of transfers from proton to oxygen. And this is a simulated spectrum, for instance, of the time dependence of the X-ray energy. And you see that when there is an emission of laser, due to the injection of laser, you should get this type of excess of X-ray production.
What if this happens before the muon decays? So how do you did that?
Sorry?
The decay of the muon, I mean, everything is very fast.
Yeah, there is a region, I will show this in picture, there is a region so that we select with the magnet to allow maximum decay from pion to muons, and there will be also decay of muons, but then you will lose the muons and then it will be filtered out. So this is the experiment is installed at Radford Laboratory. It's in the outskirts of Oxford in England. This is the region. And so next slide, I make the zoom of this region to show more in details what is the facility. There is a synchrotron 800 MeV proton, where in correspondence of this extraction line of proton, there is the Fabio experiment, and there is also another extraction line that is used for other things. This facility is mostly used for actually it's a neutron spatial source, so for the analysis of material, but it's also there are lines also to extract muons. This is more in details. You see all the other experiments installed in line, and this is part one, that is where the Fabio experiment is installed. And for the Fabio experiment, we need the muons, and the muons, they are created by making the proton the proton beam collide with the right target. Here you see a picture of the target. And from this collision, you get out pions, and then the pion decay to muons. There are two types of muon. The muon that decay at rest inside the target, they will give for the body one fixed energy. So the negative one is captured, and then the positive one emerges with the given energy that is lower compared to the one that we need in FAMU. In FAMU, we need higher momentum, and this is obtained by selecting muons that come from pion decays that emerge from the target. So the pion has to come out from the target and then decay in order to select. And this is the type of momentum that can be selected from the experiment, and we take 155 MeV. it is a pulse beam structure, so the proton, they are extracted every with a frequency of 50 hertz, so we get pulses every 20 milliseconds. And but there are pulses because protons, they go in opposite direction, so you can extract the protons on two different moments. And since the time of travel of the proton is 640 nanoseconds, we get to muon speed at half of this time, so 1 every 320 nanoseconds. This is the picture where you see that the momentum gets profound from the decay muons at 55 MeV, allowing to get about between 10 to 4 and 10 to 5 muon at the entrance of the experiment. Then one that we see will be a little bit lower, but this is the typical intensity. The experiment is made of several components. We have the cryogenic target that contains the mixture of hydrogen and oxygen. Oxygen with a fraction of 1.5%, so it's small, cannot be too much, otherwise all the muons will be captured, and so that you will not be able to see the effect with time. And at the pressure of 7 bar. The temperature that of this mixture gas is the temperature of liquid nitrogen that is used to cool the gas, and this is because you want the lowest possible temperature, so that you will not have the background coming from the kinetic, the muon transfer from hydrogen to oxygen due to just the kinetic energy of the system. So the idea would be that you quickly cool, and so you get the demands from this hypertranscritic energy only. This is of course not possible. You cannot go too much down on the temperature. You are limited by the 60 degrees, the temperature of the condensation of the oxygen that has to be remaining gas state. So this is the compromise, and we worked at about this 80 Kelvin. And then in the laser at the hypertransmit energy to excite the resonance, and this wavelength that corresponds to the 183 millielectron volt. And an X-ray detector to measure the excess of X-rays at this hypertransmitting energy. In this plot, so this we did this during the commissioning, and this shows actually why oxygen can be used as a contaminant to see this effect, because you see that the rate of muon transfer from the hydrogen to oxygen, it depends on the temperature. Thanks to this temperature dependence, then we will be able to see the excess when there is an excitation of the resonance. This is a picture of the FAMA experiment in port 1, so in the weekend port 1. And you see basically from this side, so the muon is coming from this side, and you had on the bottom the table, with the optical table with the laser that create the laser. It's one of the most complicated part of the experiment to create this energy, because it's not available. There is no laser that is available to provide this wavelength, so we have to build it with the sophisticated system. Sophisticated because it has to work at constant for long period, because we typically, for each step of the scan, we typically have 1 day, so you have to keep this high energy output laser for 1 day, and this is not simple. Here you see the picture of the cryogenic target. So in particular, this is the container of the liquid nitrogen. The gas, the target gas is hidden here. You see that in another slide. And this is the germanium detector that it's also installed for but this is for just for spectroscopy, so to understand what is which are the type of material which are present, in particular to see if there are materials that you don't want. So this is only for spectroscopy, but next slide, I think. Yes, next slide you see another view with the muon beam coming. So this is opposite with respect to the previous picture. Here you see the muon beam from the left and the X-ray detectors here that are placed around the target gas. So the target gas is hidden inside here. And the X-rays, they are emitted by the gas in this direction. So this from the right, you have the injection of laser at the energy of the hydrogen split hydrogen, and then on the front here you see also a beam monitor that it's important for the to monitor the beam condition, so the muons that enter into the gas.
Son dos pasos, entonces el primero, que inyectar los muones y producirse
Questo effetto. Sì.
And then you inject the laser. So it's in 2 steps.
It's done. There is a certain time. So once you inject the muon, it takes a certain time to internalize to the gas to get to a certain state in which you have a number, because you have a certain number of transfer of the muon from the proton to oxygen with the time. And I have a plot later where I show the time dependence of this, and you see that at some point you decide to inject the laser. So it's after action. So first you inject the beam, you have the system that thermalizes, and at some point you inject the laser to see the effect. But you have to decide a good time to inject the laser, because it must not be too late, that all the muons they already transferred from the proton to oxygen for natural let's say processes, and cannot be too early, because you risk to go into close to thermalization where there are effects that are bigger. So you have to decide the time. So we are talking about nanoseconds. So you have hundreds of nanoseconds to do this, and so it's still doable. But the last thing is injected after. And we do. I can see that. So, and we do normally, because we don't inject all the time. So we acquire data also when we don't have a laser, so that we will be able to do subtraction of the spectrum to see the effect. So this is a schematic view of the target where it's simpler to see the different parts of the experiment. So you have the muon beam, the otoscope for monitoring the condition, and then you have a collimator, so that the muons that arrive at the target, they will be inserted in the correct place inside the gas vessel. This is the gas vessel. So the gas vessel is very small, so all the rest is a tank with nitrogen, and you have the copper braid, because the cooling is done with thermal contact of the copper braid with the current. So this is the target. And then there is here a layer of silver that is used to stop, to refine the stopping of the muons. So to make sure that the muons that come from the beam are stopped in the correct place here, where there is the gas, and not in other place, because otherwise you have only background processes that disturb the analysis. So the dimension of this layer, they are optimized to increase, let's say, to have the most of the muons stopping where you have the cavity here, the laser. Because once the laser is injected, there is a cavity that I will show later, where the photons of the laser, they oscillate, so that you increase and maximize the probability of interaction between the laser and the muon the muon cartridge, and in order to increase the probability of having transfer from hydrogen to oxygen.
Good question. So because what's the energy of the muon that are fighting? Because you need to stop them. That's correct.
Yes.
So what's the incoming energy
So
roughly?
it's if, the momentum is 55 MeV.
Okay.
And this is, I can show you a plot later, or maybe I can now present it in the.
And then you do the
But it's interesting plot because this is the so for the commissioning we did the change of the muon beam momentum and let's say this region is the region where you are at the maximum of the production of the transfer of oxygen, and you have the minimum of stopping inside the other material. So it's an energy that it's optimized to increase the effect. Yeah. Okay. So just this is to see a real picture of the target from the close. So here you see that where the muon beam comes, and this is where the laser is injected, and this is the liquid nitrogen tank. The target, the gas that is smaller, so it's about 10 centimeter in dimension. Yeah, it's inside the. As I said that it's so the laser part is challenging because it does not exist a way to take this. It was not actually now since the beginning of the experiment. This 10, 15 years ago, there have been other solutions. So if there will be a next generation of experiment, there will be probably more powerful system for the laser. But at the moment, that was the best choice. So you have a non-linear optical crystal that receive two laser beam of different wavelength. One that is standard, and then with standard you want to create the target wavelength to excite the hydrogen splitting. This is one. In this plot you see the theoretical value, and they are about 6.8 micrometer. And what you do, you create this energy as with the difference different frequency generator. Means that with this crystal you can calculate what is the other frequency that you have to inject in order to have the required wavelength. And this is 2062 nanometer. And this is possible because you have a smaller frequency in output, and you see that this operation costs energy because you inject with the pump laser, you inject 7 millijoule, and with the second that's called signal 35 millijoule, and then you have much less in output. That is 1 millijoule, but that is still a big power in output. But see that most of it it's lost. So these are more let's say detailed schematic view of the LUX laser with the two wavelengths, which are first combined because they are developed on different lines. Then you have to combine before putting them in nonlinear crystal. But the interesting fact is that you want to tuning of the wavelength, tuning of the energy of the laser, and this you do it by keeping one line fixed, that is with one beam gap, and the other one tunable. And the other one that is a signal, laser, is still starting from a beam laser that goes into input to the chromium phosphorite oscillator. but the thing is that in order to make the tunability, we have the two pieces of electric motors that allow to change the position of the two mirrors that create the cavity of the dress. And these two mirrors, it's one here, where you have the medium young with the nonlinear laser. Then the laser with this path, it goes on a diffraction grating. And the first order of diffraction is used to make the reflection inside the cavity, so to create the cavity effect. And then the zero order is the output that's selected to the corrected wavelength. And so by acting during data taking on the position of these mirrors, you can tune the wavelength that you need, and you can do the scan to measure the resonance. These are other picture of the target. The target open with the copper plate for the temperature, and then with the gas vessel. You see that it's a bit gas vessel, it's small, it's inside. With the laser injection on one side, and then the muon beam comes from the top. So here the muon beam we see also a thin layer of aluminum. And inside the gas vessel, you see the cavity, the optical cavity. When the laser is injected, then from here you see better, it oscillates between the two mirrors. These are the mirrors of the cavity, and here it oscillates. And this is a simulation of the oscillation of the light inside the cavity that is done to maximize then the probability of the interaction of the laser with the gas inside the target. And so the structure here, I stress that it's with the material, it's based on the titanium in INVAR, in order to make the structure more solid and more resistant to the variation of the temperature, to the thermal cycle. As an experimental physicist, I'm to explain those. the live spark is interesting. Okay? The muon beam monitor that it's inside, that is the first thing that muon hit is this is made of scintillating fibers of 6.4 by 6.4 centimeter, this region here. And there are the two orthogonal planes, so make reconstruction of X and Y, and there is a space between fibers of 1 millimeter in both direction in order to minimize the material that is crossed by muon. And then we have the algorithm based partially on simulation and partially on data to estimate the flux of muon. You see the picture of the flux of muon in the center, and which show to be linear. So basically, number of muons as a function of the total charge measured with the scope. And the tuning of the number of the muons was obtained by tuning the magnet that are used to drive the muon from the accelerator till the target. So the main measurement is this total charge. Then we have so that in front of the mirror set we have the monitor, and then the PD collimator, the LED collimator, and then the target that are all around outside the target with gas. There are these X-ray detectors that are scintillators, lanthanum bromide, doped with cesium. And this is because it is a fast scintillator, because there will be a lot of muons, so there is pileup, and you want to minimize that. and with a good time and energy resolution. There are 34 detector units, and they are arranged in 3 wings. The central one, that is basically where it's maximum the number of oxygen X-rays. And then there are also other to recover some other that come from the side. This is a simulation that, and it has to be used to decide the position of the X-ray detector. Here, more in detail, the position of the detector, of the X-ray detector that are of 2 types that are labeled radial and mid. They are all mounts a crystal of lanthanum bromide, but they have different shape and thickness. Because it has been shown that with simulation that the thickness of 1 inch is enough to absorb the X-rays energy, but there are also other versions with half size thickness that still could be efficiently used, but they have basically less photons. And the main difference between the two is that they are developed by different groups. And one developed photomultiplier without, and one classic photomultiplier, and one silicon photomultiplier without. Here you see picture of the assemblies with the PNT without. So here you see the bromine lanthanum scintillator and the PNT without, and this is the mid assembly where you have still the scintillator here, but it is coupled to silicon photomultiplier that you see here. The difference between the characteristics is mainly that photomultipliers they work at higher voltages, so they have a higher they are fast at higher rise and fall time compared to silicon multiplier, but yeah, probably partially also due to the dimension of the crystal, the energy resolution is a little bit bigger compared to silicon PEM. So they are a little bit complementary technology to do the measurement. And the passes from the detector, they are digitized. They are digitized with the kind commercial kind digitized. So we sample this is an example of digitized pulse. So this is an X-ray. So we sample basically the voltage with the ABC every 2 seconds. With a 14-bit ABC. So from the ABC count that corresponds to the maximum on this pass, we extracted the amplitude that corresponds to the energy of the X-rays. And this we do by analyzing the derivative of the pass to look for the maximum. Now, the last 6 slides, they are on the measurement, the result of the data taking that it has been done in 2023 and 2024. This is a picture of the wavelength scanned wave. So one Gaussian here corresponds to 1 day of data taking that is taken in the same wavelength. And the scan is done in this blue region in blue that corresponds to this region in blue around the let's say around this position around the theoretical prediction that we have for this energy. So the aim is to analyze this data to decide where is the resonance to make the measurement with this accuracy, but it's a very small number. The laser show the good performance with data taking with the stability in time. You see, this is 1 day of data taking. Time to time, the laser was going remote mode, so giving different frequency, but these are excluded from the data taking. And these are the period. This is a bigger period of data taking where you see the step of the wavelength scan. and also period in which we did not take data for maintenance. And is a feature of the energy distribution that is injected in the cavity. That this is the period in which it was maximum 3 millijoule, but normally it's smaller, around 1. And this is important because from this measurement will be used to do correction, because the larger is the energy, the larger is the effect. And so when you build the resonance, you have to correct for this kind of effect. This is an example of the time in which the pulses are reconstructed. This is a key plot because based on the timestamp of the X-ray, you do the selection of the interesting region. The interesting region for us is the one that is far from the arrival of the muon, because this is the time where the system is thermalized, and then you inject the laser, and you can see the effect. And of course, you see, if you do it before, you will have bigger effect. So this is the time that we consider the best to do the insertion of the laser, injection of the laser. The time before the laser is still interesting because it contains information that is for calibration. Because when the muon is capturing the other material of the target either in the lead collimator or in the silver thickness thick layer that is before the target, you have emission of X-rays at a given energy that you can use to calibrate the detector. So this is a data-driven calibration that is interesting for establish the performance, but we also use it to do the correction of the gain of the detector based on this line. And this is an example of the energy spectrum with delayed X-rays. So the one that is interesting, you see the two peaks here, they correspond to the tail line of the emission of the oxygen. So they correspond to the signal that we observe. It's not the total signal, so it's the oxygen. So what we want to measure is an excess of this X-ray. And so in order to assess the quality of the data, we have taken also data with pure hydrogen that contain only background. And by doing the difference between the delayed spectrum, which is in black, with the oxygen and hydrogen mixture minus the background, you can reconstruct the pure oxygen spectrum, where you see clearly the two lines. This is only for data quality assessment, because then, as I said, when we do measurement, we take data with and without laser, and so we estimate the excess of X-rays by doing the subtraction of the two spectra before background subtraction. So the systematic should be less, should be smaller. And here you see the typical rate of new X-rays that we have in the data is typically about 1 per trigger. So every time that comes, it's quite a big step. So every time that comes 1 million, we get typically 1 X-ray detected in the system. And there is a difference between the sets of data points between December and September, because we increased basically the acceptance of the system by replacing set of detector with the bigger one. So still on the performance, you see on the x-axis the different type of detector. There are 34, and they are plotted as a function of the resolution. You see the first group is they are the 6 labial detector overlap together here, and there are the 28 mid detector, and these are also overlapping here. So in order to have, let's say, an idea that the data quality is good, here you see that the width of the speed that is obtained by overlapping of the detector is consistent with the average energy resolution of the single detector, that is about 12% for this set of detector and 7% for the other. So after doing this calibration, then you can overlap all detector and look for the excess in the total sample. These are plot of the variation of the gain of the X-ray detector as a function of the time, mainly of the light set, and these also are used in data to correct for the variation of gain. So this gain variation is measured and is used to correct the X-ray count in order to avoid the appearance of spurious effect that could be mislead the research for the resonance. And this is one example or one exercise that we're doing now, because we have data with laser and without laser that we will subtract to estimate the excess of X-ray production. But for the moment, we did unblind the analysis. What we have done is to, for each wavelength, we have separated the sample into two subsamples of the same size, and we have done subtraction of these two samples to make sure that there is no component due to drift or any kind of performance of the detector that would show up as an excess that does not correspond to a real physics effect. And this is what you see here: the two, the energy spectrum of the two random sample and their subtraction. And the subtraction then, so the integral of the subtraction is taken in the region where that corresponds to the region where oxygen is raised at produced, mainly between 60 and 20 kb. And this is the final spectrum where one should see the resonance. One point is 1 day of the data taking with the associated error at the given wavelength. And these points, they correspond to this random subtraction. So as it should be with random subtraction, you should have only random fluctuation on this point. And this plot is also nice because it shows that this is the estimated effect. So if there is an excess due to an effect of 3% size, the size of the effect it's not known, so we will discover how much is it, because it depends also on the physics, but also on the characteristic of the experiment. But if it's 3%, that is relatively small number, like, so hopefully will be bigger, but still with the 3% effect, so it should be good. So it means that one should, with this systematic uncertainty, should be able to see it. Exactly. So this is the end of my talk, where I showed you what we do with the pharma experiment to explore the structure of the proton with an interesting and complex detector where all the components they behave in data taking according to expectation, but we don't have yet finalized the analysis for the to measure the resonance. We will do it finally, hopefully, with the first attempt by the end of this year, but there will be also more points to come by the end of next year, 2026, where we look forward to see the result. So that was the end. Thanks a lot. You see here the nice pizza that we got. So pizza, Napoli, Buenos Aires, Parisha, all together. After mix, interesting.
The tango is missing there.
Tango, not the
So, good. I don't know if questions.
Sí, bueno, la verdad que sí, me re sorprendí porque no me esperaba de qué se trataba.
Esa pieza tan larga.
Sobre todo porque al principio estaba un poco asustada con las unidades de energía hasta el slide 26 que empezaste a hablar de no sé qué cosas que uno entiende.
¿La qué?
Sorry.
No, puede saludar.
No, because I noticed that you use kilojoules and this kind of.
Yeah, there are different factors
Units,
of
yeah.
energy that can be misleading. When I say energy output, actually, when I say the millijoule, this is the energy of the laser. That it's an intensity, a measurement of the intensity of the photons. So the more photons you have, the more probability you have to interact with the hydrogen. But the hydrogen split, it's, yeah.
So, unfortunately, we couldn't see the final result.
No, in fact,
So,
this
you
is
have to come back. But in any case,
next time.
in any case, you must see an excess, right? I mean, it's not possible that you don't see.
So the effect is there. So the problem it will be there. The problem is how big the effect is, as I said, because the uncertainty is 3%, 5%, 10%. Actually, I show two different plots because here I say this is the line, this is the expected effect is 3%, but then, for instance, in the simulation, I showed also before a plot. The plot where in the simulation you plug in simulation an effect of 10%, which is bigger. Now, this is distributing over time. The point that we see in the plot is integrated, so it's but you see the effect is small. And for me, the most interesting part would be to be able to see the effect in this plot, because it's here where you see that you have the evolution of the X-rays in the time, and then you have a bump. Because when you show the last plot to just the integral and you see 1 point, it can be anything. This is for me, it's really the signature that you're seeing an effect. And here it's difficult to have, it's more difficult to have systematic uncertainty because it's a dependent, time-dependent measurement. The problem is that here I'm quite sure that we will not be able to see because it will be too small because it's divided in time slots. So
you need the excess, and then only once you have excess, then you can obtain the fit, obtain the parameters, and all that. The final result will
yes.
be.
The final result, we will have to implement something intelligent because I think that the effect will be there, but it will be very difficult to see like this in the plot. So by doing cut selection, most probably we will have to invent something because there are also effects that are energy dependent, as I showed before. Yes, this kind of plot. So the larger is the energy of the laser, the larger is the effect. So most probably, now this is not yet done, but most probably you will have also to introduce some convolution also with this kind of spectrum to put together all the effect, because otherwise it will be difficult to reconstruct perfectly the resonance. And then we will have a technique of sliding windows to suppose, because based on the assumption that you do on the signal, you will have different, you can adjust different points, and then the resonance can be easily lost. So the analysis will be quite complicated. So that's why they are not yet results. But this was, it's unfortunate thing that this confirmed that by a simple cut-based analysis, it will be difficult to see the resonance. Then one will have to invent something. as well.
I have a quick question about the laser. So you said the PS electrics there,
Yeah.
you know, and then, well, maybe on the coffee I will ask you about the first one, but here the second one, yeah, that's the one you make actually the resonance of the laser, right? And so the cavity.
Yeah, the
Right.
cavity is between these two mirrors. These two mirrors. Yeah.
Okay.
This is
Okay.
rotational and this is linear. So,
Okay, that's where you move.
yeah.
So, okay, I understand. Okay, and then that allows you to scan because the piece moves really little.
Yeah,
But still,
micrometers. Yeah.
but still you are able to scan the whole stuff. And my last question, following up on the laser, is that you mentioned that actually by doing this non-linear mixing with the crystal, you lose a lot of power. You lose a lot of power. And you just said that if you could have more power on the laser, your signal would be stronger. Is there a way you can gain something here?
Yeah, there are. So when this was chosen, was selected among the different type of materials, and the big energy that you put, it's a stress for this material that at that moment was the best one. But there will be other material most likely that will allow to work, but also to have less loss. Yes,
Yes, I'm thinking about the loss.
I'm not an expert of the laser, but the colleague that worked on the laser, they did the detailed presentation of how the system can be improved to increase this, and it will be the base for the proposal of the follow-up of the experiment that is not yet decided because in principle it finished next year, the data taking, and then I think that if we find a resonance, something, an indication of a resonance, then we will be able to make a new method of intent to continue the experiment and to do all the interesting part for the optimization of the output energy. But without that,
How much it costs people?
how much it costs? I don't know, but I don't know. I don't know, but I was trying to click this. But, you know, it says, so this is the size of the exactly entire experiment. Probably the one that is more costly is really the laser part. Yes, the rest for the there are commercial part. Also, this German detector is commercial. Then for the construction of the target, with the company with yeah, no, I don't know much, but it's in the range of the cheap experiment.
Yeah.
Also the time it runs.
Yeah.
the time in fact when I also tried to ask the collaboration if we could go to a different beam line. On one end, so for instance, in Germany, in PSI, but there they are making a competitor experiment. But there you would have to pay. But and one of the reasons to stay live is because historically they are hosted there. So, but then you are a little bit subject to the integrity of the structure. But this is for the moment. It's not really the stopping. I think after a long period of time, there was the data taking with the laser was finally done from 2023, and it's now the challenge part of the analysis.
I think that the answer to the question from you, I think the whole thing is happening in microseconds for the neurons.
When when the muons are finished.
Yeah,
Decay.
the lifetime of the muons, and you finish in a couple of microseconds.
Yeah, this is it.
It was a question of
And the time window that we acquire is four microseconds. After 1 microseconds, we the laser.
Grazie molto. Hay que tomar café para el gigante.
Y preparar el estilo.
Hay que parar el
Muy bueno. Io per sé, perché mi sono guardato io, lo